All right, thanks everybody. I'm Baxter Eaves. I'm from Redpole, which is a tiny little R&D consultancy that I kind of built so I could do Rust and probabilistic programming full time. And I'm going to be talking about LACE, which is a tool that we've recently open sourced. It's a Bayesian tabular data analysis tool. So it takes in a table. A table can be loosely defined as something that can be loaded into polars. It learns a joint distribution over that table using something called Bayesian non-parametrics. And then once you have that joint distribution, you can ask about conditional distributions and ask a lot of questions about your data set really, really, really quick. And so our goal with LACE was to optimize for the process of exploration and discovery and learning about what your data can and can't tell you. And so LACE does a lot out of the box. If you're coming from kind of the standard data science ecosystem, you know that every time you want to ask a new question about your data, you kind of have to reach for a different tool or a different model. But that's not the case with LACE. We're trying to be as self-contained as possible. And so there's a lot to talk about, and I'm not going to be able to talk about everything. So to learn more, check out lace.dev. So I'm going to be working through a couple of these capabilities using a analysis on a satellite's data set. Each row of the data set is a Earth orbiting satellite, and there's features such as orbital mechanics and logistics types of things like what was the launch vehicle, where did it launch from, who operates it. And so the data that you give LACE doesn't have a whole lot of constraints on it. Again, it needs to be loadable into polars, because we're using polars behind the scenes, and you can pass in different types of data in the same data frame. So we support continuous data and categorical data as integers and strings, and count data as integers. We handle missing data just fine. So if you have missing data, just leave it missing. You don't have to impute. There's no imputation happening behind the scene. And in fact, we can do inference on missing data, including missing not at random. And I'll talk about that here in a little bit. So one thing that you will have to do is provide LACE with a codebook, and the codebook is how you tell LACE how to model each of your features. So what type is the feature, what are the priors, the hyperpriors, and so on. And we can infer the codebook pretty well from the data frame, because data frame has a schema. And you can use this as a template and adjust it as necessary. But once you have your codebook, you pass in your polars data frame, and then you're good to go. You've initialized a model from the prior, and then we can run our fitting procedure, our markup chain Monte Carlo procedure, and that's a kind of an animation of it going on a single sample. And now we have a model. And so now that we have a model, we can start asking questions. And one of the first questions we always like to ask is, which questions can we answer? And we can get to that by asking about the statistical structure of the data set, and we can ask about that a couple of ways. So we can use something called dependence probability, which is a model specific quantity, or we can talk about mutual information, which is an information theoretic quantity. And here I've plotted, I've used our Python library, which is written in Py03, to render the dependence probability over all the feature pairs. And so we have a couple of groups of mutually predicted features. So up here, this blob is orbital characteristics, and down here we have logistic characteristics and things like that. So we can do prediction in LACE, and the way that we do it behind the scenes is we compute the likelihoods, and then we kind of optimize along that likelihood function. So if you're interested in, and you're working in something where knowing quantifying risk and uncertainty and multimodality of your predictions is important, you might as well just look at the likelihoods directly, look at the distribution of your predictions, and that's pretty easy to do in LACE. And so we're looking at the Python library here just to save space, and so I'm computing a few different things. So I've got the log likelihood of the orbital period, which is how long the orbit takes in minutes here, over a range of values, and this is just the marginal likelihood. So the likely period of any old satellite, basically, and it might be hard to see, but that's the blue line here. So there's a bump of mass over the low Earth periods and the middle Earth type of periods, and then the geosynchronous periods over here at 1440 minutes, or basically 24 hours. We can condition. So we can say, compute me the likelihood of period given that the class of orbits geosynchronous, and that gives us this orange line. So it's flat basically across the board until we get to the geosynchronous periods now. And we can condition on values being present or not present. So we'll compute the likelihood of the orbital period given that that longitude radians of geo is none. And this is a column that's only present for geosynchronous satellites. So we see that the green line, which is that line, is got low Earth orbiting satellites and middle Earth orbiting satellites. This figure over here on the right shows how we can combine likelihood, use likelihood for prediction. So the black line is the likelihood, the red line is what the predicted value would be, so the maximum likelihood here. And these gray lines show the likelihood from the reference of each of the posterior samples. So you get a sense of how much the posterior samples disagree. We can also do anomaly detection. So anomalies use the likelihoods behind the scenes, and to compute the anomalousness of an in-table value or something we have observed, we can use this surprisal function. And so we'll ask for the top 10 most surprising satellites by their expected lifetime. And so the most surprising is this International Space Station. It's a low Earth orbiting satellite in the roughest region of space. It's got a really high expected lifetime. You and I know that that's fine. But the LACE doesn't have that extra knowledge, so it's thinking it's surprising. But so what if we thought that this was an error? Typically what you would do with normal machine learning tools is you'd have to go out into your data set and fix that and then kind of retrain. But with LACE, we can just edit the cell in place because it's online algorithm. And so we call edit cell, and we can immediately rerun the same query here. And you'll notice that the International Space Station is no longer in there because we've fixed the error. We've made it no longer surprising. And so LACE does a ton more, and I haven't even gone into depth of the things that I've shown, and we'd be happy for you to use it. So check out lace.dev. We just released v.2 yesterday, and feel free to reach out to me on LinkedIn or GitHub. Thank you.
All right, thank you very much for the talk. I have the impression that LACE is a really good contribution to the statistical computing ecosystem in Rust. So yeah, I don't see any questions here right now, but I'm sure they will trickle in. And please, oh wait, there's one here. I think we have time for one question. Is this using a method similar to Gaussian processes to form the predictions, is the question.
It's using a method called probabilistic cross-categorization, which is a hierarchical non-parametric model that uses Dirichlet processes. And I don't think that David Dahl is in here anymore, but we're using one of his sampling algorithms, which I was kind of excited to see that he was a presenter. Yeah, we're using mixture models so we can have different types for the different columns and things like that. So I'm happy to talk more in depth about that very complicated algorithm afterwards.